Whatever we have here doesn't matter. As long as the diode is on, the output is going to track the input, and it's going to be the same as it minus this constant value. So what if I directly connect a load here? I directly connect a resistor. Well, if I draw the input here and I draw the output signal, I'm going to get this. At the beginning, the input signal is going to be small, so the output is not going to track anything. The diode will be off and is going to be 0. When the voltage difference between the output and the input reaches 0.8, 0.7, the turn-on voltage of the device, then the diode turns on and it tracks the input and it tracks the difference here up until the voltage difference again becomes 0.7, 0.8, and the diode turns off again. Turns off again, it's off, it's off, it's off, it's off, it's off again until the difference here becomes VD on. At that point, it turns on again and it turns off again right here. In this stage, it's off. In this stage, the diode is on. It is off and this on, this off again. Well, is the desired result? Did we create a DC supply? Well, not really. But I assume we're in the right direction. We don't have negative signals here. Alright. Now, do I know a device that can hold a voltage for a longer period of time? Well, I know that a capacitor can do it. Let's plot some voltages here to see what it does. Well, if I connect capacitor here, remember that as long as the device is on, it doesn't matter what we have here. The voltage here minus the voltage here must be equal to a constant value. The voltage is off. The diode is off for this period. Again, when the difference is large enough, the diode turns on, and when it reaches this point, the output signal is going to become lower than the voltage at the output, and it's going to want to reduce the difference here. Well, if the difference here is small, then the diode is going to turn off again, but earlier this time, over here. This means that the output voltage is going to be a constant value, and it's going to keep being constant indefinitely. Why? Because the difference is not going to be large enough in order for the diode to turn on again. So the voltage will be off, the voltage will be on for a little while, and the diode will be off again indefinitely, forever. This seems to be a step in the good direction. However, no actual load is a capacitor, so our loads must be some type of resistor, some type of resistive device. So what I'm going to do is I will say that, well, I simulated the DC current here, a DC voltage. Therefore, what I'm going to do is I'm going to connect a resistor in parallel to this capacitance. Well, let's see what happens when the diode is off this time. When the diode is off, no current is going to obviously flow from here to here, but our configuration reduces to what? A simple RC circuit. Why? Well, I know that the diode is going to be off, so no current flows from here to here. Now, I have a capacitor here and a resistor, and the capacitor dissipates its energy on the resistor. And if I were to draw the output voltage here, this is from the basic circuit theory, the output is going to look like this. It's an exponential. It's going to be a constant value, the voltage here of the capacitor at the beginning, times the exponential of minus t over tau. Tau is the RC constant, time constant of the RC configuration. It's calculated in seconds, and it is responsible for how steep the voltage at the output is. Now, what we are going to do is an approximation. Again, studying engineering, you're going to find many approximations like this. Turns out we can do many wonderful things with such approximations, as long as we are somewhat accurate. Again, this means that for a small t over tau here, the output is a straight line. So the output is going to be this, VO, the voltage here, times 1 minus t, right, over tau. This is nothing but a straight line. And if I were to now draw the outputs and the input on the same axis, the diode would be off for this time. It's going to be on again. Again, doesn't matter what we have here, as long as the device is on, the output tracks the input up until this point. Diode turns off again from this to this. This is when we have a RC circuit. I deliberately draw it as a straight line because I assume we are in this region here and not an exponential. The diode is off from here to here. Again, the voltage difference is not large enough for the diode to turn on. When it gets large enough here, the diode turns on again for a little while. Up until this point, the input is tracked again, and the behavior again is the same as here. And this repeats forever. Again, this is the circuit, and I notice that I have somewhat of a DC output here. Not quite, but it's simulated well enough. And I notice that we have some kind of wave here effect. This is known as a ripple effect. And what we want is the ripple effect to be very small so that we can simulate DC voltage properly. We don't want the ripple effects because it introduces signals in our circuits that are unwanted. If I delete some stuff here, I see that when the behavior is of RC type, the output signal is going to look like this. VO, V0, is going to be what? Vin minus VD on, alright, the same difference here, is the highest point, times 1 minus T over tau. T is going to be the time that the diode is off. This is the decay of the capacitor's voltage. Again, this is off. The diode is off for this region and this region, etc. The maximum voltage here at the output must be equal again V in minus VD on. And if the ripple is small enough, because we actually want small ripples, the time that the diode is off is going to be equal to tau in, the period of the input signal. Why? The time from here all the way to here, if the ripple is small enough, it's going to be about the same as from here to here. This is a very small time difference. then I can safely say that if I take these values and replace them here, that V out minimum over here is going to be equal to V in minus VD on times 1 minus tau in, the period of the input signal over tau. Now, I'm interested in the voltage difference from here to here so that I can reduce the ripple. I'm going to introduce a new concept, the ripple amplitude. The ripple amplitude will be 1 minus 2. So it's going to be this minus this, and if I do the algebra, I get this result. This result is beautiful. It says to us that I can meaningfully measure the size from here to here just by knowing the input signals amplitudes, just by knowing the turn-on voltage of the diode, knowing the frequency of the input signal, and knowing the characteristics of the load and the capacitance of this configuration. We want to reduce it obviously to simulate DC properly. And so let's check an exercise now to see what we understood. I have a somewhat of an interesting exercise here. I have a laptop and I want to charge it with DC voltage obviously. Again, if you want to charge a battery, you want a DC voltage. Under a nominal 4 voltage, it consumes 20 watts of power. We connect this to the wall. Let's assume we're in Europe, so we have 220 volts and 50 hertz. The transformer transforms the voltage from 220 to 10 volts. Again, the frequency is the same here, 50 hertz. And I have a diode device here. I connect in parallel a capacitance here, not C1, and I am asked to find, as a circuit designer, the minimum capacitance so that the ripple is small, very small, 0.1 volts. Right, first of all, I can simulate the load of the laptop by a resistance. How? Going to say that the mean power consumed by the laptop is going to be the mean voltage under it consumes it squared over the resistance load. Then the resistance load is going to be 0.8 ohms. Now, the peak voltage of the input here and here is going to be what? 10 over 2, 5 volts. Why? Because these 10 volts is the peak-to-peak voltage. So the peak voltage is going to be 5 volts. Now the input signals period is going to be 1 over 50, which is 0.02 seconds. And now I'm ready to plug in my numbers on the ripple amplitude equation. This is 0.1, this is 5, this is VD on 0.8, 0.02, the tau in, R1 is 0.8. And if I do the algebra here with these numbers, I get this result. The capacitance is 1.05 farad. This is huge. I cannot easily accommodate a capacitor like this without making it very, very large, very, very big. As circuit designers, we must be very careful in order to make our circuits practical. I could use a full wave rectifier, but that would cost me an extra 3 diodes. If I choose a half wave rectifier, I'm going to have 1 diode, but a very, very large capacitor. So what should I do? Well, that's why we are engineers. We have to see the advantages and the disadvantages of which configuration to use when, and choose the best and the safest one. If you learned something valuable today, subscribe to the channel and let me know down in the comments below so that you can support me and I can keep making these videos for you. Study well and take care.